Now that we looked at the troubles in high-performance computing, we're going to look at TensorFlow and first answer a very small question. TensorFlow, you may know already, is a library actually for deep learning. So why I'm talking here about using TensorFlow for high-performance computing. So just to hint you, for all of you who don't know deep learning, very strongly simplified, what deep learning does is it just takes some input vector of data. You can think of events, you can think of whatever particles pt, and this just maps it to a y. That's it. It's a function. I mean, to say just supervised learning basis is the same thing. And basically, what we do here is, instead of scientifically, we try to find this kind of transformations, like analytically, but basically for complicated transformations. Numbers, how we want to get from this image to the left to the numbers on the right. We're not interested in how this exactly works. We just want to have this input to the y. And this is just done simply with fitting a very high capable function to x and y. This is basically machine learning. There's not a lot more. Meaning, also, if you heard of these neural networks, they can approximate any function. If you just build this, a neural network, just give you an idea. You basically take some random matrices and then nonlinear function, and then you just create a network by applying the function, have this random matrix on your input vector, and do that over again and over again. So just a bunch of matrix multiplications. That's deep learning, nothing more. And that's why we call it high performance computing, this whole matrix multiplication of neural networks. Or that's why a neural network library like TensorFlow has to be very efficient in high performance computing, because neural networks are just high performance computing. Now, what is TensorFlow actually? As mentioned, it's a deep learning library with a Python API, so we can call it from Python, but it's actually mainly implemented in C++. It is supported by Google, but it's a mainly open source library that is highly popular on GitHub right now. I think one of the top 3 or 4 most popular libraries with these 150,000 stars. And it consists basically of 2 parts. One is the famous part. This is the high-level API for building neural networks. That's this, but we don't care about that because there are so many good tutorials and examples out there and documentation. If you're interested in machine learning with TensorFlow, this is all very well covered. What we care about more is that TensorFlow also has this low-level API with, let's say, NumPy style syntax. And in this talk now in high-performance computing, we will solely be interested in this low-level functionality. One very small disclaimer on TensorFlow. If you're talking about TensorFlow, there's now TensorFlow 2 out, and this is the one you should use since a year, but it's in a way completely different from TensorFlow 1. You can still find many tutorials, so if you see words like placeholder, session, run, feed tick, etc., that's TensorFlow 1, and this works differently. You won't understand that, let's say, if you follow this tutorial, and you can't just forget about it, basically. So what is TensorFlow? In a very short line, it's like NumPy, but it has a JIT compiler like Numba, the thing we've seen before to compile a Python function. So it means, by default, if you call just a TensorFlow function, this acts like NumPy, with the small difference that it also has directly already GPU and CPU support. We just call it tensor instead of array because it's fancy. And actually what we have here is a so-called egotensor, which is really just a wrapped NumPy array. It can also be converted to one by just calling .numpy or by calling np.array on tensor1. It means also we can directly use even the np calls on an egotensor and we get a NumPy array. So it's quite compatible in that way. If you're just running things normally without any JIT, without anything fancy. And an example of how it looks like is below if you add two logarithms. It's all the same as NumPy basically. Now, it is a little bit different though than NumPy. There are a few different names because, yeah, they're fancy. And in general, TensorFlow tries to be way smarter. So it has more overhead, as we'll see later on. A simple call is not just in NumPy, it calls just this one implementation for an addition, while TensorFlow tries to really look up what's the best implementation to add this specific tensor. Can we maybe add some of them? It also has some currently experimental, but will more be used. It's also used in PyTorch, if you know that. More of a dispatch computation, meaning that it basically tells, okay, add this arrays, and it already continues to execute the Python code until it needs these arrays. Actually, it's just up there. So in the back, the arrays can be computed while the Python code continues to function and so on. So it has, let's say, more overhead because it tries to be smart about stuff. And there's this simple rule that if you have more overhead to try to be smart, you're inefficient for small things, but you're more efficient usually for large things. The main part, though, so far we're like NumPy, a little bit smarter. The main part, though, comes from the tf.function JIT. This is a decorator, as we've seen before with the number, as you can see on the right. We can just put this on any TensorFlow function. And now what happens actually is that if we now call this function addLog with two numbers, what happens internally is it does this JIT. So instead of giving our numbers into X and Y, as we would think of normally happens in Python, it gives in two symbolic tensors. They're like, you can think of algebraic elements, and executes this function with these algebraic elements, algebraic tensors, and just looks basically what operations, what TensorFlow operations are executed on these algebraic elements, and returns in the end basically an algebraic expression. So this means if you now decorate this with a function, before we've seen we can have tensors like a NumPy array, they have a value, we can add them. If we're inside a function and we decorate it, the tensor doesn't have a value because it's an algebraic tensor, let's say, but it has static properties, like it has a shape and it has a d-type. So what it does, we're feeding in an algebraic expression, and it returns an algebraic expression, which is built using only the TensorFlow operations. I mean, or the overloaded plus and times and so on. But we don't use any Python logic because we can't, because the things don't have a value yet. We're just building up this expression. Or as we can also see it is, we're building a computational graph. This is what actually happens inside this decorated function. So to give you an idea how that could look like is if we're summing A and B and C and D, and then we multiply the two things. This is what basically what is returned in a way, or what we have in the first run. It basically creates the graph here on the right. And then it remembers that graph, remember JIT, it compiles it. So it gets like a compilation in the sense it gets a specific implementation or representation, which is in this hand a graph for this function, and it forgets about all the rest. It forgets about all the Python there. It forgets about the print statement. This is just executed in the very first run. It just remembers calling this function A, B, C, and T means we need to add A and B, we need to add C and T, and we need to multiply the two results and return the results. That's what it remembers. And depending on the input, it can just it sometimes needs to recompile, as we will see later, but usually just tries to remember. So if you check how often will compiling now appear if we execute this code, it will be just once, namely the first time that the function gets compiled, and afterwards we only have the function's equivalent to this graph execution. This has, as mentioned before, the implications that if you use TensorFlow, we cannot use any Python logic in there that depends on the value. So for example, if you're doing the one on the thing on the right, if you say if A equals smaller than 0, do this and this, we can't do that because A is just a symbolic tensor. It's like, okay, I'm an expression and you can do some operations on me, but only TensorFlow wants. So TensorFlow restricts itself there to a subset, which means only TensorFlow stuff, but there are many, like, as you will see, that it can do stuff, but no Python things. So we built this graph just with TensorFlow elements. And this may be a little bit uncommon on the first place when thinking about it. Meaning also we can't use the .numpy call here because it doesn't make sense, because we can't convert it. It's just an expression. So if we want to implement the above, there are two ways. I mean, the best, of course, if you want to have an absolute one, then we just use the tf.apps. And that's it. Otherwise, what we could also use is a conditional, which is, it's called tf.cond, and it acts like an if-else statement, but it's really then part of the graph. So we use, so for Python, just to build a graph, like sticking together the elements, but the graph itself is just TensorFlow things, but TensorFlow support things like TensorFlow if-else, or a where. To give you an idea what can be used for the graph is cond or switch and switch case, which are if and elif statements. We also have a while loop, which lets us implement fors or whiles, if you like, or something like a map. However, we do not want to usually put everything to a graph. Remember, the graph, this should be the optimized representation of our computation. So we do just want to have the dynamicity, the logical flow in there that we actually need for our computation, but not the rest. So not how to stick it together. We still can use some Python logic on the object. We can't use the equal, for example, because tensor doesn't have a value. So we can say if tensor A is equal to 42, because it's just a symbolic tensor that will have a value later on. But we can check the identity. So if the object, the is really checks the identity of the object. So if two objects are the same, not if they have the same value, but if they are in memory the same object. For example, we can check if it is known. So if it's just none, or if it's a tensor. Or as the shape. We could also see this more in the tutorial, which we know beforehand, usually, but sometimes also we don't know it yet. Like if it is some, we try to say, okay, take all the elements that are larger than 5. And we had some randomization before, then we don't know yet how many elements we're going to take. So it's going to be none, let's say, statically. So having a little bit looked at that, just to make sure what really happens. The function is called with something there. Ilya, you want to say something?
Yeah, I wanted to ask, actually, can you go to the previous slide, please?
Sorry?
Can you go to the previous slide, please?
Yes, sure.
No.
Wait. No. This one.
Yeah, this one. So actually, the map, if I understand correctly, this map fn, it allows to map certain function with the elements of the tensor. Is it correct?
Yes, it just means it applies any function to the tensor, but basically, let's say it applies. There are two things. This map fn just applies the TensorFlow operations in that function to the elements, not any arbitrary Python function. But so yeah, because if you let's say if you want to have this optimized representation, then we need to be inside TensorFlow. As a side note, which I can take ahead, is there is also something called tf.py function, meaning we can have arbitrary Python code execution in there as well. However, as soon as we have this, remember, we're losing the optimization, the specialization on just using the subset of optimized TensorFlow operations, and we're again slow. Mm-hmm. So that's, I mean, as usual, the trade-off.
Okay. So can we, so from what you say, we cannot optimally calculate average of the two elements, right? So in one, right? For example, so we have an array, and yes. I want each element to be the average of the two neighboring one.
The average of two neighboring. We can do this with array operations, actually.
Okay.
like you would do in NumPy maybe. So you add basically two arrays and just like slightly shift it to the left, slightly shift it to the right, and divide it by two.
Yeah. Okay. Okay. I mean, I give it as an example. So often
Yes.
you can use some, you know, more
Yes.
specific things requiring the manipulation of individual elements of the tensor. But okay, thank you.
So there is also more dynamicity because there is also stuff like folding and stuff, which then automatically takes the elements from the left and to right, or sums up and things. So let's say there is a limit in what you can do. Practically, though, you can go very far with it. So it takes quite a lot of time until you can't do the things anymore, I find.
Okay, thank you.
So what exactly happens is, again, the function is called with a signature, so with some inputs A, B, C, and T. This can be tensors or this can be Python objects. If they are tensors, they get converted to the symbolic tensors, and just the D type and the shape is remembered basically, because if it's a different D type, it has to compile again. If it's a different shape, it up to a certain point also has to compile again. If it's a Python object, this is also important. It cannot convert a Python object, even a number. It does not. It's actually good that it doesn't do that. It cannot convert this to an algebraic expression. I mean, this doesn't make sense. If you're given a list, what kind of expression should that be? So it just takes basically the equality for that, meaning that if you put in the number 1 or the number 2, this will every time compile new because 1 is not equal to 2. If you create the tensor out of it, that's a different story. But if you just use a Python number 1 or number 2, then it's retraced. Side note, what we can also have is so-called structured tensors. So if you, for example, have a list of tensors, and this is recognized as being, you can't just replace all the tensors in there with symbolic or dictionaries and so on, which is quite a useful feature. But in general, if you put in Python objects, pay attention. It usually just retraces. So if it has a signature, it remembers the signature and it traces the function. We see on the right now this add mode with now 2 print statements. One is the Python print, and the other one is the TensorFlow print. And the difference there is the print in Python is just run exactly once if we compile it in the first time, while the TF print is now an operation. This is a TF operation, so every time we execute add mult, or let's say, to be precise, every time we execute add mult, which executes the compiled graph that is associated with add mult, tf.print will be executed as much as some AB will execute it and some CD and so on. Now it builds that graph, it caches his remembered your signature, and on the same go, it also executes the graph with the input that we've given. So if you call add mult, we don't really realize the steps. Just on the first time, builds the graphs and runs with the graph, and afterwards, if we give in again similar inputs, then it just runs the graph and doesn't compile at the end. But we don't really notice that as a user, except some larger time if we run it for the first time. So as mentioned before, the Python objects are different. If we give in, for example, TF constant of 5 and TF constant of 3, it just compiles 1. And if we give in 5, then and we give in 3 afterwards for A, then these are 2 different graphs. So to be sure, in its way of thinking, any TensorFlow operation means it's dynamic in the code. Anything non-TensorFlow is treated as static, meaning we're going to look at 2 examples, how things actually look like. So if you, for example, have a global number, and if you have some random NumPy random uniform, what this actually looks like to TensorFlow once it compiles is it just means A plus 42. It doesn't keep a reference to the global because it's just 42. It's a Python value. It's not TensorFlow, so it just takes the value that there is. And for a NumPy and NP random uniform, it just calls that once, gets a number, and adds this to the graph. So the above function actually looks TensorFlow like this, because as remember, so every TensorFlow operation is dynamic part of the graph, everything else static. What we can do, if we want, for example, the random to resample every time, we can add a TensorFlow version of this. Now it's a node in the graph with TensorFlow. So this will now, every time, create a new random number. This is the difference. NumPy or Python, they're static. Run once, fixed to the graph. TensorFlow, it's an operation. This is executed every time we rerun this function now. And last but not least, the global. What we can have in TensorFlow, and this is also a crucial difference, for example, to number, is global variables that have a state in between runs that we can assign a value and change it. So if we now run the function for a certain value, and then we just assign a new value to var1, then the output of the static Python function will also change. So this is like a global value that is respected. And this is crucial for any kind of machine learning training where you have variables inside your code that you can change. So let's say in high performance computing, it's good to have inputs and process them, but sometimes you want to have variables globally that you can change inside the already built graph. So this graph, to look at it from a different point of view, this is, as I said, an algebraic expression basically of what we're doing, which is a full symbolic representation of our computation. Thinking back, we have a full symbolic representation of our computation from beginning to end, fully defined, everything as specific defined as possible. So if you look back now at the first part about all the things about the parallel code that is very hard to get it right, about race conditions, about getting a specific optimized representation of something, being static about things, we can now fully use this, or with the graph we defined very, let's say, very clearly what we want to do, which operation to execute when, meaning the conclusion of these slides was, let's not do this work ourselves, let's delegate that. And since we built this graph, since we clearly told TensorFlow what we want, and TensorFlow now knows from A to Z what to do with it, it can just take the graph and do this stuff for us. And that's the full power of having the graph. So these are two examples of graph. The right one actually you can also produce yourself with TensorBoard. And the left one, as an idea, what TensorFlow can do now is it looks at this graph, which we just define inside the function. We can say, okay, let's do this on CPU1, let's do this on CPU2. Now it's also very obvious. We have this line going over, so we need to have a send there, we have to have a receive there. We have all the dependencies and stuff visible. This graph is so powerful because it defines how everything. Now we can schedule everything. We know what to move where. We can figure out whether it's worse to do it on GPU or not, whether it's worse to split between CPUs or not, because we know all these things. Also, maybe a remark on race conditions. Sometimes it's still not clear what should run first. And there is basically the idea that if you run the Python code in your function, then this is how things will be executed as well in the graph. It's a guarantee. So we don't have any race conditions in there. It runs as you expect it in Python, which is more noticeable if you use assignments of variables inside functions, but this is already advanced. Furthermore, with this graph, we can do many optimizations now. We can fuse together operations. Some operations have specialized implementation. As you remember before, these instructions, we can have very specialized implementation to take, for example, the logarithm of something, add it, and takes exponential again, or something like that. And if you now see, oh, we have a logarithm, then we have a sum, then we have an exponential, we can now fuse these things together now that we have the whole view of it. We can see that we're computing the same in two different places, so we just need to compute at one and plug it in the other thing. We know that there is constant, so we just need to calculate these ones, and so on. With all the graph optimization, with all the graph, we can do many optimizations. This is also called the grappler in TensorFlow. And furthermore, it's so easy to distribute things on CPU and GPU. All we need basically now is just limited by how smart is TensorFlow, but we delegated the whole workload. What we can also see, how we can also see this thing is a declarative versus an imperative coding style. Imperative means if you do NumPy or normal Python, we say add A plus B, the computer adds A plus B. Then we say, okay, now take B and add this to C. Okay, and the computer does all these things. So we have to tell them exactly what it does. But what we've done here actually by building this graph is we've done it declaratively. We just told them which computations we want them to be done, but not what actually to do. We just say add A, B, and then add B to C. But how you're doing that, when you're doing that, and whatever, we don't care about. Hands of control, we define the graph, and it's up to TensorFlow to schedule that stuff. Another interesting thing that automatically pops out of this is automatic differentiation, meaning if you have this full symbolic computation and every operation knows its own gradient, we can just go along the graph, use the chain rule, and we get the derivative. Let's say an exact expression for the derivative, which is way more stable than any kind of numerical implementation. One thing that I didn't notice and note so far, and it's just a bit to mention it, there is a feature called autograph. If you've been closely watching, then I already always had in TF the function is autograph equals off. TensorFlow can additionally automatically convert some of your Python code to TensorFlow operations, meaning you don't gain anything. You can always write the same as well with tf.const and stuff. It sometimes just looks a little bit better. If you use tf.function, by default it uses autograph. In general, I would advise against using it because we never know how exactly to translate things. Maybe it works. One other thing to do is you can also use the tf.autograph to code of my function, then it automatically applies to the autograph and it gives us this code. We can use it. I'm not saying you should not use it, but be aware, it's just something now different. Now, using TF function with the autograph, it's not that just TensorFlow functions get dynamically inserted, but that some Python functions are made dynamically, so we can use the thing on the right. And this is just, I find it very confusing because you're never sure what it actually does. So it's way cleaner to start autograph off, only TensorFlow functions are traced. So to give a summary of my talk, we know computer architecture, it's complicated. We need parallelized stuff. We have many things in there, and we want to have things as static as possible. TensorFlow is basically an equivalent to NumPy normally, but it has this very strong JIT decorator that symbolically evaluates our code first and uses the static graph in the end to implement many optimizations, to distribute it, to use the whole power that it can do. So with that, we're really delegating all this stuff to TensorFlow. So next thing is we're going to have a tutorial. I think we're going to have a few minutes break in between. This is an iPad notebook tutorial. I will say this afterwards, but first let me ask you, and there we will look at how the aspects actually look like. It's sometimes a repetition. But first, are there any questions? And thanks for your attention.